Hello, everyone. How are you doing? Yeah. Okay. Today I'm going to give the talk how we scale a distributed SQL database to PB level. Yeah, a little bit about myself. I'm working for TiDB, and I'm the maintainer of TiKV and also RocksDB contributor. I used to write a book about MariaDB internal. And for the past decade, I built TiKV and TiDB from the scratch with other colleagues. And this is my GitHub and the technical blog. Yeah, this is today's agenda. We mainly have 4 sections. The first one, I'd like to briefly introduce the importance of database scalability for your business growth. And the second section, I'm going to introduce a little bit about our product, TiDB, and its adoptions. And the third part is focused on the challenges we have faced during the past decade when we were building this product and when we support our customers. And the last section is about QA. If you have any question, yeah, we can have conversation. So let's move to the first step. First part, business growth is a great thing for companies. Yeah, we have more users, more tenants, and we deliver new features for our customers, for our new users and existing users. And definitely there are more data collected from your users. And from the technical perspective, there might some challenges because for your application server or for your backend database, there are more connections. It means more requests, more data, and more data need to maintain. So let me give a real example to show this more specific. Bolt is a fast-growing mobility company from Europe, and they have around 100 million users. Yeah, it's a great number. And they provide service in more than 500 cities. And since the pandemic, their business has 400% growth. Yeah, this is a great thing for them. But from the technical perspective, they also faced some challenges. In total, they have hundreds of terabytes to PB level data volume. And every day, they will have 100 service deployment. And they need to do 100, more than 100 database changes. I mean, the schema change or data migration every week. And every month, there are more than around 5 to 10 terabytes new data generated. And they use MySQL. So you can imagine, definitely they hit the single MySQL instance size limitation. And for some large tables, if they want to add some index, it will take them 2 weeks. Yeah, this happened in their case. And backup, you can imagine how long it will take. Yeah, and the result is they need to maintain hundreds of MySQL instances. This is their story. So when facing the growth challenger, the traditional solution is sharding. Yeah, you shard your database, you shard your applications, but this also means you need to have some compromise. Yeah, you need to rewrite your application's code. You need to compromise some functionality, like if you want to query some data across the table. And You can imagine how to make a consistent snapshot backup for your database if you have shared your data across multiple nodes. All this is a reality. If we choose this solution, we need to face. So for the past decades, we focus on solve these issues. We want to build a SQL database. It's scalable. It means you can simply just add nodes for this system, and then everything can go. And you don't have to change your application code, and you can use all the SQL you want. And at the same time, even there is a large amount of data, we want to achieve the low read and the write tail latency. And of course, the system is high availability. So this is the effort for the past decade we have paid. Yeah, this is where TiDB comes from. So what is TiDB? TiDB is an open source project, and you might be familiar with TiKV. Yeah, it's a CNCF graduated project. Actually, TiKV was created as the storage layer for TiDB. And there is a funny story about TiKV open source. Actually, we open sourced the TiKV at 2016, April 1st. It's a fourth day, yes. Yeah. We don't notice that. After we posted this message to our social media, and everyone don't believe it. And we realize, oh, it's April 1st day. Yeah. And benefit of this is, even several years has passed. I remember this exact date. And this is TiDB's architecture. It's compatible with MySQL. You can think it as a size unlimited MySQL. And your application can connect to the TiDB with MySQL protocol. And MySQL's ecosystem tools, you can just use it. And TiDB is a disaggregated compute and storage architecture. And so you can scale the compute layer or the storage layer, respectively. Of course, it's a high availability system. And the PD is a metadata center. So if you know TiKV, actually PD and TiKV is known as the TiKV. Yeah. And meanwhile, we also have a column engine which can replicate the data from our TiKV engine and in real time. So the TiDB can query some heavy joining or heavy aggregation queries. So let me show two use cases. One is Flipkart, which is the largest e-commerce company in India. And a few years ago, they will search a scalable database for their Big Billion Day, which is Black Day, similar here, like Black Day here. And they want a database that can just add some nodes to the system, and then the throughput of the whole system can increase at their demand. So several years ago, they come to us, and now TiDB has, with Flipkart, has experimented 2 years, Big Billion Days, yeah, and everything goes well. And this is a test report by Flipkart. They use around 40 machines to reach more than 1 million QPS with the tail latency in single-digit millisecond. And the other use case, this is a large cluster with more than 500 terabytes compressed data. And this is a online social platform. They have more than 300 million registered users. And what impressed me is there is 1.8 trillion records in single one large table in this case. And TiDB is also used in some North American users like Databricks, Pinterest, and LinkedIn, and Plaid. Plaid is a financial SaaS company. Okay, let's move to our third part, is about the challenge we have faced and our solution. From the architecture, you can see the PD part is a metadata center. The storage layer, we have multiple TiKV nodes. The data is stored here, and the metadata is stored over a PD layer, which is a cluster. And what PD do is it needs to monitor the health of the whole cluster. If there is some like TiKV is unavailable or has some issues or network issues or disk issues, and then the PD need to understand it, need to know it, need to recognize it, and then do the balancing. Because data is replicated across multiple TiKVs. So single TiKV's failure doesn't impact the service. And the other way, the other task the PD need to do is they need to cache all the data range, location, and leadership to the metadata center. So if there are, so the requests come and it can know where the connection need to connect. Because we partition the data into like hundreds megabytes size level. So if there are, why we choose such size is because we want the schedule is very fast, and if there is high workload to one single partition, we can split it and rebalance it. Yeah, and PD also can monitor the workload of different data ranges. This is happen when TiKV has some request, and TiKV will collect statistics from different data ranges and then report all these statistics in real time to the PD center, to the metadata center. And then the PD can know which part is hot, which part is not, and then they can balance the workload automatically to make sure the workload is evenly distributed. So you can see there are a lot of things PD is taking responsibilities. So the first scalable issue we met is how we can make the metadata center scalable. So we did some optimizations, like we can make the PD's follower can also serve the request. And meanwhile, there is some issue with adapter. Okay. And meanwhile, because there are multiple tasks PD is handling, so we disaggregate the PD into several services and deploy them into dedicated resources. So we can make sure each of them can scale respectively, like the TSO, which is the time-stamp service, and the metadata management service, statistics, and the scheduling service. And as I have just mentioned, hotspot issue is a common issue for a large distributed system. If there is single node or minority node take the majority workload from the whole system, then this node can be the bottleneck of the whole system. So how to handle it I just mentioned that we can collect, the statistics and the workload of different data partitions and report them to the scheduling service. And then the scheduling service can, can trigger the split and the balancing command to the TiKV node. But there is also a hotspot issue that the write hotspot issue that we cannot, automatically handle. That is, I will show you an example. If the data is always append to one single partition, append to the tail, we have no idea. We cannot, automatically split them and balance by this way. We cannot handle it. And for the read part, we basically are the same with the write part, but there is some slight difference. For example, if there is a high throughput for a single data partition, it's already small. Like there is a 100 row table, and it's very hot. And we introduced a feature named load-based split. And we can collect, which row and which data range has specific high throughput, and then we can report this information to the scheduling system, and then split. Even the partition is already small, like 100 rows. We can split it in 10. Each one has 10 rows, like that, and then distribute it to multiple TiKV nodes. Yeah, as a large system, there are hundreds of nodes. There are, millions QPS for the whole system. So we don't want to, if there are any issue, we don't want to. We want to know what is the root cause. Yes, which query caused the issue, or which node is the current bottleneck. So the observability is very important for a large system. And we did a lot of effort on this. And you can monitor the cluster level information, like how many nodes you have and how much data of each node has, and the resource usage, the latency distribution, and the QPS. And even we have the proportion of the different statements. Meanwhile, if there is a hotspot issue I just mentioned, you can find out from here the CPU of a single node or the I/O of a single node is very high. But how to locate, how to identify which SQL or which table has this issue? Yeah, this is the next step. So we introduced the key visualizer, which can show the throughput of a different data range. And then from this picture, you can see there is a bright line, which means this data range has high throughput. And you can tell which database, which table, and which index caused this issue. Yeah, this table, this is a bad example. Just I have mentioned, this write hotspot issue we can't, handle it automatically because it's a bad design for in terms of distributed system. All the you can imagine all the write of this primary key index will happen in one place. So from the SQL's perspective, we can monitor the slow queries. In our system, we name it the top SQL, which means this SQL, they consume a lot of resources. And we also have the SQL statement, which can show you the dominated SQL query pattern from your application. Yeah, this is with statistics from the frequency perspective. So after you have located, for example, you have located the the top SQL, and then you can click here, and then we can show the execution plan of the SQL, and what's the query plan, and each step, how many rows it has scanned, and how many resources it has taken, and how much time it has taken. And the next challenge is the operational challenge for a large database, especially SQL database. So you can imagine, I want to load a large amount of data from S3 into the system and serve my application. I want to back up the whole system to make sure, even we have multiple replicas in TiDB, but I also want to, most of the customers want to back up their database periodically. And what if we add index for a large table? Yeah, this all are operational challenges for us. And for the load data, we introduced the distributed execution framework, which can translate the ParQuery file, SQL file, CSV file into the TiKV's data format, access table format, and then ingest to our storage layer. And you can label the compute node. So this heavy job can just happen on this node you have labeled. Let's see a result, test the result. This is a table from our real customer, has 55 columns with 5 indices. And there are around 100 terabytes data from the S3. And they use 12 TiDB nodes. Each node has 16 with CPU. And it took around 31 hours. It's not bad. But I want to highlight is if you have more TiDB nodes, the total time can be linearly reduced. And the next is adding index. It's similar as the import. We reuse the distributed execution framework. And the difference between import and add index is the data is already in the system in TiKV. So we can just scan the data and generate the final asset files and ingest to TiKV. Meanwhile, there might be some new insert for this table. So we need to do the incremental KV, the index KV, and write into our system. And this is a test result from a table with 40 terabytes data. And we create the index with 14 TiDB nodes. And from the first line, it takes around 1 hour to finish the job. And you can see the last line. This is a single node mode. It means the add index is just run in 1 TiDB node. It takes around 14 hours. Yeah, it's linear scalable. And the second row is about use one single statement to add 5 index at the same time. It took around 1 hour and a half. It's not 4 hours. Because all the index is from the same table, so the scan just happened once. And the backup is also a challenge for a large database. And we want to make it scalable. So from the storage layer perspective, each TiKV will, for the full snapshot back, each storage node will upload the snapshot asset files to S3 simultaneously. And we also introduced the rate limit on our TiKV internally, and we can limit the resource and the throughput of each TiKV used by this backup job, so we can make sure the latency of the online traffic is acceptable. Yeah, meanwhile, we also have the incremental backup. If you already have take a snapshot for backup, and then each TiKV node will incrementally upload the incremental changelog to object storage. So let's see a test result. We tested the full backup for large database. The first has 100 terabytes data, and the second has around 300 terabyte data. And they have different numbers of storage node. And each node has, for the first cluster, each storage node has 2.6 terabytes data. And the total time of the full backup takes 45 minutes. And the second test takes around 1 hour and 4 minutes. And it's not 3 times of the 100 terabytes test because we have more storage nodes. And actually, the total time cost by backup it has a relationship with how much data each storage node has. Because from the mechanism, you can see all the storage nodes can do the work simultaneously at the same time. The recent challenge we are facing is a noise neighbor challenge because as a scalable SQL database, our customers, they consolidate multiple MySQL instances into their single one TiDB clusters. And there might be multiple applications running in the same systems. So if there is one application that has large queries or heavy queries, and this may impact or affect other applications. And also the other widely used scenario is SaaS company. We have multiple SaaS company customers. They have multiple tenants, and each tenant may have different workload. So how to make sure this noisy tenant, if there is, cannot impact other tenants. So we introduced the resource control feature, which is a feature can control the user from a specific tenant or application. And basically, the idea is we have different strategy from the compute layer and the storage layer. And we introduced the resource group concept. You can bind multiple applications into one resource group. It means this multiple applications share the resource in this resource group. And you also can allocate a dedicated resource group to a significant like KA customer or KA tenant. And from the storage layer, we use the priority-based scheduling, which we use mClock algorithm to satisfy the resource allocation. And from the SQL layer, we use like SQL flow control for different users, from different users in different resource group. Let's see the test result of a use case. The left part is we don't introduce, we don't apply the resource control feature. And the blue one is we simulated the order applications. And the yellow one is the report application, which has a huge impact for the online traffic. You can think. And the right side of the picture is about we apply the resource control into the system, and the order application has no impact, and the latency is the tail latency is kept in 15 milliseconds. Yeah. Okay, this is all I want to share with you today, and yeah, I believe the time has passed 30 minutes. Thank you for your time, and if you want to discuss, or discover how TiDB can solve your problems, you can scan this QR code. And this afternoon, my colleague Matthew will, from the application's perspective, how to scale your microservice with our scalable, stateful backend database. Thank you. Any questions?
Hey, thanks for the talk. I had a question on, does TiDB also support replication? If you have a multi-region deployment, do you replicate automatically across regions as well?
Your question is about multiple region deployment?
Right, yeah.
OK. From our practice, we have multiple TiDB clusters. We use CDC to replicate the changes across region. Yeah.
Got it. And the CDC has to be set up by the client, or is it done by TiDB automatically?
CDC is a component of TiDB.
OK, sounds good. And one more question I had was, what about strong consistency versus weak consistency? When you write, does the data, the data read, does it follow strong consistency checks? Or
Sorry?
How does consistency work with TiDB? Is the writes, are the reads strongly consistent?
No, read and write.
Yeah, I know, but
yeah, read and write strong consistency.
OK,
yeah.
Got it. Cool, thanks. That's all I had.
Hey, first off, thank you for the talk, and huge respect for what you all have built here. I work in this space as well, and this is exciting, but also a very technically challenging problem. So the question that I have is about the PD part of that architecture diagram. Is it just like one? Yeah, thanks for going to that. Is it just like one? I know you showed like one of them's a leader and the others are followers. Is that like one raft group? Or is it multiple? Is it possible for there to be multiple leaders?
Right now, it's a single raft group, and we are working on to offload the data into TiKV part, which can reuse a multiple raft architecture.
Okay,
yeah.
That makes sense.
This can further scale over metadata center.
Cool, thank you.
Thank you for your question.
Hi, thanks for the talk. You mentioned backup and backup time, and I was curious, do you have any numbers or ballpark on what restore times and what the downtime for restores would be in similar scales?
You mean the RTO of restore?
What do you mean?
You mean the restore time?
Yes, so when you have the backups and then something happens with the cluster, let's say, and you need to restore it from the backup.
Yeah, it's a similar, because it's just the reverse procedure of the backup.
Yeah.
But the specific number is not the same, but they are the same level.
Okay.
And it also depends on how much incremental change log you have. Yes, it differs, but they still at this the same level.
Right. So you have incremental restores as of you roll back. Or
yeah. If you open your full backup, it happens. You can daily or weekly, but also you need to open the PITR, the incremental change log. Yeah. Time is over. I can chat with you offline, definitely.
Sure. Thank you.